challenges associated with applying life cycle assessment. So first of all, life cycle assessment is a structured environmental assessment. And so a lot of times we find that it can be confused with life cycle cost analysis. So life cycle assessment is an environmental assessment method, and it's somewhat analogous to life cycle costing insofar as we're concerned with the entire life cycle of an asset. And so the goal here is to actually assess all the environmental impacts over a life cycle and throughout the complete supply chain associated with that life cycle. So in terms of how we actually go about trying to quantify environmental impacts in life cycle assessment, we're tracking inputs and outputs over a life cycle. So the inputs will be things like material, energy, and resources. And the outputs will be things like waste and pollution, as well as the products that may be generated, for example, at the end of life if recycling occurs. A lot of times I describe this as, you can think of this a little bit about balancing a bank account insofar as their inputs and outputs, but instead of just one, say, monetary flow, we're looking at a whole set of material and energy inputs and waste and pollution outputs that are essentially in different flows of resources and pollution. So one of the challenges, as you can imagine, given that we're tracking all of these different kinds of flows over a life cycle, is ensuring that different studies can be compared and ensuring that similar practices were applied for every study. And to help us with that, there are some standards and guidelines out there, and the most commonly cited is ISO 14040. So the ISO here is the International Organization of Standardization. And one thing to point out is that this is a very general standard because it applies to any product, not just, for example, asphalt pavements. And so a lot of times we find that the standard isn't quite sufficient to ensure that studies are done in very similar ways. In any case, we still use these as an important guide. So here I've listed this particular, standards that apply to life cycle assessment, so 14,040, 44, and then there are a few more in there, and I know we'll hear about EPDs later, which also are subject to ISO standards. But one thing I want to point out at this first one for 14,040 is that 41, 42, and 43 really go through the steps of life cycle assessment, how we actually undertake a life cycle assessment. And so here's the figure based on ISO's figure for how we think about going through a life cycle assessment. So we think about first defining a goal and scope, then conducting an inventory assessment. This is the accounting stage where we track all those flows, and then impact assessment, and then interpretation, which is most important at the end but can occur throughout. So if we want to define key steps in that first step of goal definition and scope, we have to think about defining the purpose of the study, and then also carefully defining the function or service of the evaluated system. And then also thinking about what needs to be included in the study or what can be excluded from the analysis. And we refer to this as the system boundary. And one of the things to consider is that, for example, a roadway interacts with lots of other systems, whether it's a vehicle system or the transportation network in general. And so we have to define where we're going to stop doing our analysis, because it could be essentially infinite. And those are some of the things we decide in the scope and system boundary. For the life cycle inventory assessment, this is where we do the actual accounting, tracking those inputs and outputs. We often think about quantifying materials and energy, and then other key resources, maybe water, for example, going in. And then pollution in the form of air pollutants, water effluents, and wastes, as well as co-products. Co-products are things that are produced alongside the system that we're interested in. If we're doing an LCA of an entire pavement system or roadway system, co-products aren't necessarily relevant. But if we think about asphalt and doing an LCA of producing the asphalt material, we have to think a lot about co-products, because asphalt is produced alongside many other products that come from crude oil. And so in those cases, we have to think about how we're going to apportion impacts to just one of many products generated by a production system. But one thing that is sometimes hard to wrap our head around is that not only are we tracking the direct inputs and outputs from our system, but we're thinking about the entire supply chain associated with those impacts, inputs and outputs. So the example I like to use for this is diesel fuel. I would wager that there's no LCA that doesn't include diesel fuel, and that's because everything requires a truck for transport at some point. And so let's say our life cycle assessment includes diesel. The way to think about how an inventory works is that we track the actual quantity of diesel consumed over the life cycle, but then we have to connect that quantity of diesel fuel with a life cycle inventory that shows us what the impacts of producing and using that diesel fuel are. And so this is the example I provide here, where we'd include diesel production starting all the way back in petroleum exploration and extraction, and ensuring that we model the impacts at the combustion stage as well. So after we've conducted our inventory assessment, we end up with a vector with lots and lots and lots of flows. And it's really hard for us to interpret those flows. What do they really mean? And in life cycle assessment, we're really interested mostly in understanding the impacts on human and environmental health. And so in the impact assessment step, we take that vector of inputs and outputs and we turn them into meaningful indicators of environmental and health impacts. We often think about some broad areas of concern in life cycle assessment, so impacts to people, impacts to ecosystems, and depletion of resources. And this is just an example of some impact categories. So these are different categories of environmental impact. And I've started here with global warming. And then we can think about how those different impact areas actually affect people, ecosystem, and resources. The way we do this is that our inventory is comprised of many, many flows. So what I've shown here are a number of, well, just one input of fossil energy and lots of outputs, pollution outputs like carbon dioxide, nitrous oxide, and particulate matter. And we associate those flows with actual impact categories. So the example I've highlighted here are greenhouse gases, CO2 and nitrous oxide, for example, and those have effect on climate change. The reason I chose to highlight these is I also want to point out that life cycle assessment asks us to consider many impact categories. But what we find in the literature is that many studies that are life cycle based are actually footprints. Footprints only examine one impact category, the most common of which is climate change. These are referred to as carbon footprints. These footprints are useful, but they don't tell us the same kind of information that life cycle assessment does because they don't tell us about trade-offs across different impact categories. But it's important to know the relationship between what a footprint is and what a life cycle assessment is. So how do we actually take those pollutants and turn them into impact indicators? Most of the time we do something called characterization. Characterization turns those pollutants into indicators using some kind of scientific basis. And I'm just going to give you one example, going back to that climate change impact. So for greenhouse gases, we turn them into CO2 equivalent. That's our indicator. That's where carbon dioxide equivalent is what gives carbon footprint its name, carbon, because it's carbon dioxide equivalent. And we use a characterization method called global warming potential. And just as an example, each of these greenhouse gases shown on this slide have a global warming potential. And that global warming potential tells us how to translate a mass of a particular gas like methane into a mass of CO2 equivalent. And this is a simple multiplication step. So I just want to indicate that many of our impact assessment methods rely on these kinds of characterization factors, where we basically turn a pollutant into some equivalent quantity of another pollutant, so we can sum them together and be able to report indicators that are more easily interpreted than a life cycle inventory. So finally, interpretation is this other step that we conduct, and it can occur throughout, but it's most important at the end because it basically tells the reader or the consumer of a life cycle assessment what the conclusions and recommendations are that can be taken away from the study. And those conclusions and recommendations are shaped to some extent on essentially the quality or the limitations associated with the study. So I've given a very generic overview of how a life cycle assessment is done, but of course the pavement life cycle is quite unique. So I've here mapped the previous figure I showed about a generic product life cycle onto the pavement life cycle. And so in a pavement life cycle, we always think about material acquisition and production, construction, maintenance, and rehabilitation, use, and end of life. Now, the confusing part about pavements is that we often don't just demolish a pavement and don't rebuild it, right? So a lot of times we're actually going through a maintenance, rehabilitation, and rebuilding effort. And so we're often passing between use, end of life, and construction, maintenance, and rehabilitation over and over. And of course, recycling of materials can be crucial. That recycling can occur directly, so meaning that it's a closed loop. We basically demolish a material and reuse it in place. Or it could be an open loop where we actually incorporate recycled content, for example, from other product systems. That might be from other sources of RAP, for example, but also could be entirely different industrial systems if we're using, for example, supplementary materials or alternative sources of aggregate, just as an example. In a complete pavement life cycle should consider material extraction and production, the construction process, and that includes both equipment use as well as transport of materials and any induced traffic delays or impacts on users that have environmental consequences. During the use phase, there are lots of different ways that a pavement interacts and has an effect on surrounding systems. That includes rolling resistance of vehicles, impacts on things like stormwater quality, impacts on urban systems like heat island effects, and things like lighting demand for lighting a roadway. So the way that the material choices or the way that we build can affect lighting requirements. And so all of these are things that we could include or maybe should include in the scope of a pavement life cycle. So how has LCA been used to evaluate infrastructure and transportation systems, particularly pavements in the past? Well, if we look at the literature, we see an extensive focus on comparing material choices or designs. There are some examples of carbon footprints or LCA being used as part of roadway procurement processes. And then we have more broadly seen LCA for transport infrastructure using comparison assessments, usually trying to compare across transport modes. But perhaps more important for understanding pavement LCA and what the state of the art and challenges are right now are looking to the critical reviews of pavement LCAs that have been undertaken. So in the scholarly literature, we see quite a number of critical reviews which have basically reviewed previous LCAs to try to understand what their findings are, but also what the limitations are. Nearly all of these critical reviews, that is, show that the focus has been on comparing material choices, and that the scope of analysis has largely focused on materials rather than the use phase. Recent studies have increasingly considered the use phase. So the trend is changing, but we do see the bulk of studies really focusing on material choices. So these critical reviews also found a few other important insights. First, the selected functional units. So functional units are basically the measure by which we think essentially products or systems are comparable, often ignore the actual function or service provided by the system. And the reason this is important is that you can miss performance characteristics that are actually crucial to understanding the performance of a system and what's comparable. Additionally, these critical reviews have identified a lack of regionally specific data and lifecycle inventory data sets. This means that, for example, a study that's conducted as an example in California, where I am, might rely on lifecycle data sets from Europe. And so we know that these are not correct, but because of a lack of regionally specific data, we find studies often rely on data sets that are geographically or temporally inappropriate. And then finally, many studies have lacked comprehensive impact assessment categories. They've actually been footprints, meaning that they've looked, for example, only at energy or maybe energy and carbon footprints as examples of the two most common impact categories considered in these studies. So from some of these critical reviews, we can also identify challenges for LCAs of pavements, and these challenges help us identify best practices for future studies. So LCA methods face challenges associated with allocation. So allocation is this issue of how we handle systems that generate two or more products. There are two allocation conditions. The first is recycling, and the second is co-products. I already mentioned what a co-product is, but if we look at asphalt pavements or especially RAP, what we're really concerned with is this generation of recycled material, which has a second product life, or maybe a third, fourth, or infinite product lives. And we have to figure out how we're going to apportion the impacts or benefits of using recycled content or generating recycled material among these different product systems. So the key idea is if we ever generate more than one product, we have to think about how to divide up or attribute impacts among those different products. So some of the goals that have been laid out for allocation methods in the past are one, that we want to incentivize practices that actually reduce environmental impacts. And we actually want to have a pretty holistic picture about what that means. So that could include considering the different industries or businesses affected by the allocation methods we recommend. We want to prevent double counting of benefits or impacts, meaning that we don't want to pick a method for allocation that allows us to basically create, I would say, imaginary benefits from among product systems. We want to select methods that are easily understood or interpreted, and it's best if we can actually try to capture causality in terms of what impacts are caused and how. So there are actually a suite of potential methods that can be chosen. This is a limited list I provided here. They include what we call the cutoff method, loss of quality method, closed loop, 50-50 or other split, and a substitution or avoided burden. I'm not going to go through all of these, but what I'm going to do is I'm going to talk about what I consider sort of the boundary conditions for the different methods that we choose. And at sort of the most conservative is the cutoff method, and the most optimistic is the avoided burden method. And so pictures, I think, are much better than words to describe what's happening. So what I've shown you here is a life cycle of two products that are connected through recycled materials. So this is exactly, you could substitute here virgin asphalt and recycled asphalt if you wanted to apply it directly to this example. And what I've shown here is a cutoff method, where we basically attribute all of the impacts of virgin material production to the first product that uses it. And then that product, the only benefit that is seen by providing recycled content for the next product life cycle, product 2, or pavement 2, is reduced burdens associated with disposal. Product 2, on the other hand, is burdened with the recycling process itself, but has the benefit of reduced virgin material production when it comes to impacts. The drawback for this method is that it does not incentivize product system 1 to be recycled, because product system 1 isn't attributed really much of the benefit of recycling. The benefit, though, is that it conserves total emissions, and it's a very transparent method. It's easily described, and it's very clear what was done. On the more complicated side of things, but also the more optimistic, is what is the avoided burden. So this is a bit harder to describe, but the idea here is that if I have a product system, and what I've shown you here on the y-axis is environmental impact, and on the x-axis is essentially time, you have the production and use of a system, and at the end of life, you have some recycling process that occurs to provide material to a second product system. So in step 1, you just see a life cycle of product 1, although we know that the recycling of the material in product 1 is going to product 2, which is why I've shown that barrier between product 1 and product 2. In step 2, what I'm showing you is the fact that by recycling product 1, we avoid impacts from virgin material production for product 2. Okay, so that blue area is what we call avoided burden. That avoided burden isn't real in the sense that it was never there to begin with, but in theory, because we've generated recycled content or recycled material, we avoid that burden. And then in the final step 3, we basically credit product system 1 with avoiding all of those impacts associated with avoided virgin material. So that green bar that's negative there basically says now we get to, product 1 gets to take credit for all of that avoided burden that's occurring in product system 2. There are some drawbacks to this. So let's talk about benefits first. It incentivizes the use of recyclable materials today. So product system 1 is going to benefit just from having recyclable materials. The problem is that it doesn't incentivize product 2 to actually use that recycled content because the credit's already been assigned to product 1. And we can't really guarantee that recycling is always going to occur. And so we're crediting some environmental benefit that hasn't yet occurred. And of course, for pavements, we have pretty long life cycles. And so assuring that 30 years from now something's going to happen, for example, is pretty challenging. So the reason I say that these two methods bound our allocation options is simply that that we often, we either do this cutoff method or this avoided burden method or something in between. Because we can imagine here, for example, for avoided burden, that maybe we decide to split that benefit 50-50 between product system 1 and product 2, right? And then we try to solve that incentive problem. So that's just an example of how we can basically think about these two as boundary conditions on our allocation choices. So, of course, if we're thinking about systems that generate large quantities of recycled or recyclable materials, such as RAP, the choice of allocation method can have significant influence on the impacts we actually assign to a product system today. And the recommendation that we often arrive at is that methods that actually conserve mass with respect to burdens or impacts should be preferred. Thus, starting with a cutoff approach and modifying it to figure out how we want to assign credit between product systems is probably better than an avoided burden approach. On the other hand, the avoided burden approach has a great benefit of incentivizing the use of recyclable materials and, if done correctly, also incorporating recycled content. So, that was a deep dive into a very complicated issue. Life cycle assessment can be complicated, but I think allocation issues are some of the hardest to figure out. So right now I just want to go over the characteristics of state-of-the-art assessments, which is a broader view. And these emerge from those critical reviews that I talked about before. So first, a state-of-the-art assessment needs to include a comprehensive scope of analysis from the standpoint of life cycle stages and impact categories. That means the use phase has to be included. It cannot just be a focus on materials. Most state-of-the-art assessments try to answer sophisticated or complex questions. For example, questions that might be answered at the network level for roadway networks, or which include dynamic processes over time. And often they're going to answer questions about things like pavement management or innovation at the technology level. The other thing that is characteristic of these state-of-the-art assessments are capturing important interconnections within the LCA scope, things like pavement vehicle interaction or other use phase effects such as heat island. Or I'm so sorry, there's a typo there. Heat island, and I'm not sure what that was there. And then finally, studies that are state-of-the-art often include uncertainty analysis. And this is important because we're modeling a product system that has a very long life cycle, and we're not always sure what's going to happen in the future. So since we can't predict the future, including uncertainty analysis on things like durability or performance, for example, could be very important to understanding the validity of a study's outcomes. And so finally, these are the same characteristics that would be recommended as best practices today. So what is state-of-the-art right now is also what we'd recommend as best practices. So these are some of the key references I cited, especially with respect to critical review and allocation. And here's my contact information. As Yaning said at the beginning, I'm very happy to respond to questions that come my way via email.
Thank you very much, Dr. Kendall. That was an excellent presentation, gave a really good overview and really provided a good picture of some of the challenges that we face right now. We are out of time, but I would just like to ask one question that came from audience. We have a number of questions, and I will be emailing you those questions. And again, as you mentioned, the audience are also welcome to email them. But one question that came is related to carbon credit, and the question is, if product has some carbon credit, such as biofuel used at mixed plant, how and when carbon credit is taken into account, at construction phase or only at the end of life?
Well, so for the bioenergy example, the way that would be accounted for, technically, if it's used at the asphalt mixing plant, for example, it would reduce the carbon intensity of the resulting product at that stage. So credits in general actually should be, the elegant solution is to apply it to the product itself, so the biofuel itself. So when that biofuel is used, the credit could be applied right then. There are more complicated answers to that, but in general, credit assigned to a product should be applied when it's used.
Okay. Thank you very much. And if you could just stop sharing your screen, we'll have our next speaker go ahead and share their screen.